Okay, so this is our probability chapter, and then in this section, we're going to discuss some of the basic concept of the probability we need um, to understand the probability. We're going to, see some basic formula, and the key concept of this section is, whenever we try to find the probability of any event, the answer would be always in between 0 to 1. But let's say the probability of an event is 0.001. What does that mean actually? And then sometime, we also have to use, word like odds. So here we're going to see how odds are related to the probability as well. So some of the basic terminology we have to know uh, for the probability are event, simple event, and sample space. Event means it's a collection of results or outcome of a process. For example, let's say you are flipping a coin, and whenever you flip a coin, you can find either head or tail. If you flip a coin one time, your output would be just a head or tail. But if you flip a coin more than one time, the output could be head first time, tail next time, or head first time, head next time. So there are so many different options. All those options are called event. So the collection of results or outcome of a process is an event. Okay. Simple event is an outcome or an event that cannot be further broken. For example, the very same example we can use, the head and tail. If you just have to flip a coin one time, then your answer could be either head or tail. There is no further breakdown. So that's called simple event. And then sample space is, the sample space for a procedure consists of all possible simple event. For example, let's say our goal is to flip a coin just one time. Then in our sample space, we could have head or tail, two different events. That is a sample space. But if we flip a coin twice, then our sample space could have head first time, head second time, head first time, tail next time, tail first time, head next time, tail first time, and tail next time. So these are the four different options available, and that is called sample space. Okay, to understand this further, let's take example here. In the following display, we use B to denote a baby boy and G to denote the baby girl. So first of all, let's say if we are trying to see a single birth, let's say that's a process, then example of event is could be a girl or maybe a boy. That's a simple event. One girl. It's a one simple event. And then sample space, in this case, it could be boy, it could be the baby could be boy, baby could be girl. So the sample space is B comma Z. Let's look at the process is about 3 births. Then the example of event is, out of 3 births, 2 boys and 1 girl could be possible. Maybe you could have 2 girls and one boy could be possible. Those are the example of event. Sample space means all the possibility. You can see all the possibility here. Could be boy 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 all 3 times, could be boy boy and girl, could be boy girl ball, and then all these options could be available. That's called sample space. And with one birth, the result of one girl is a simple event. That's what I was trying to explain here. And the result of one boy is another simple event. They are individual simple event because they cannot be broken down any further. With 3 births, the result of 2 girls followed by a boy is a simple event. When rolling a single die, the outcome of 5 is simple event. So if you roll a die, just one time, single die, then outcome of 5, because in a die you could have 1, 2, 3, 4, 5, 6, anything. So outcome of 5 is a simple event. Not a simple event. For example, let's say with three birds, the event of two girls and one boy is not a simple event because that can be done in three different ways. Could be girl girl and boy, could be girl boy girl, could be boy girl girl. So you can further break down your case. That's why it's not a simple event. Okay, and sample space means all the possibility. So these are the notation we use. P stands for the probability for any event we're trying to calculate. Let's say A, B, and C are some events. Then P of A denotes the probability of event A occurring. Meaning, let's say you are flipping a coin, and in a coin you have head and tail. Then what is the probability of finding the tail? That's how you denote your probability. Probability of finding the tail when flipping a coin one time. That's how we denote a probability for any event. And so remember, whenever we calculate the probability of any event A, it should be always greater or equal to 0. It cannot be negative, and always less or equal to 1. So it should be in between 0 to 1. And if the probability of any event is more close to 1, that means that probability of happening that event is very certain, very likely. If the value of the probability is close to 0, that means it's unlikely. The probability of happening that event is very unlikely. And if the probability is, let's say, 0.5, which is probability is 50-50. Okay, so always you have to keep in mind the probability of any event should be in between 0 and 1. So we're going to discuss about 3 different common approaches for finding the probability of any event. For example, the first one is called relative frequency approximation of probability. And to calculate the probability using this approximation method, so you have to know number of times that event happens divided by total number of times the process was repeated. We are going to see one example. So just remember this formula. Okay, probability of any event A is equal to the number of times A occurred divided by number of times the process was repeated. Classical approach is, if you are trying to find the probability of any event A, one thing you have to keep in mind, all the events in that sample space should have equally likely. For example, if you are flipping a coin and there are two sides of a coin, head and tail, then to get the tail or head, they have equal chance. In that type of example, in that type of situation, you can use this formula that's called classical approach to probability. Requires equally likely outcome. This type of example, you can calculate the probability of that type of event. For example, here probability of getting head or tail can be calculated by number of ways that head or tail in this example can occur divided by number of different simple events. Okay, so what is the probability of finding the tail when you flip a coin? So how many tails are there? One tail. So how many events are there? Total 2, because there is a head, there is a tail. So probability of finding a tail in one flip is half. And you can use this formula whenever you have equally likely outcomes. Okay, subjective probability. The probability of any event, the probability of event A is estimated by using knowledge of the relevant circumstances. So you already know some data, and based on your data, you can always find a chance of happening some event. That's called subjective probability. Sometimes finding the probability for actual event is not possible, so we use simulation. Okay, a simulation of a procedure is a process that behaves in the same ways as the process itself, so the similar results are produced. Probabilities can sometimes be found by using a simulation. So whenever we try to find this probability, if there our answer could be in a simple fraction or in decimal form. So whenever it's in decimal form, the standard rule is we can round it to the three significant digit. Okay. Okay, law of large number. As a process is repeated again and again and again, the relative frequency probability of an event tends to approach the actual probability. So that's called law of large number. Okay, what does that mean is, let's go back to the same example. There is a coin and there is a head and there is a tail. Okay, first time you flip a coin, let's say you got head. Second time you flip a coin, again you got head. Third time, again head. But if you keep repeating this process, the law of large number says eventually the probability of getting head or tail, it should be approximately half. Okay, so as a process is repeated again and again, the relative frequency probability of an event tends to approach the actual probability, because the actual probability of head and tail is half. So no matter how many times head comes initially, for the large number of repetition, after repeating the same thing again and again, eventually the probability of getting head is close to half. You have to keep in mind the law of large number applies to behavior over a large number of trials, and it does not apply to any one individual outcome. If we know nothing about the likelihood of a different possible outcome, we should not assume that they are equally likely. The actual probability depends on factors such as amount of preparation and the difficulty of the test. Let's look at some examples. Relative frequency probability, airline crashes. Find the probability that a commercial airliner will crash on any given flight. And these are the information we have given. In a recent year, there were 39 million commercial airline flights and 60 of them crashed. So the probability of airline crashing based on this data is number of airline crashes divided by total number of flights. Because there were 16 crashes out of 39 million, this is the estimation of, this answer is we say it's a probability of airline crash, but it's actually the estimation based on the previous data. Okay, here the classical approach cannot be used because the two outcomes, crashing and not crashing, are not equally likely. Okay, a subjective probability can be estimated in the absence of historical data. If we don't have historical data, then we can use subjective probability. Let's look at another example. In a Pew Research Center, okay, I hope it's a Pew, P-E-W, Pew Research Center survey, randomly selected adults were asked if they have seen or have been in the presence of a ghost. 366 of the respondents answered yes, and 1,637 of the respondents answered no. Based on these results, find the probability that randomly selected adults says that they have seen or been in the presence of a ghost. So you need to find out the probability of who's, based on how many of them said yes. Okay, probability of yes is equal to, total, and then divide by total number of cases, which is 366 plus 1,637. And then, out of 366 of them said yes. So divide 366 by total number of cases. That gives you, the answer for probability of saying yes. So the total case is 2003, total number of responses, and if you divide 366 by 2003, the answer is 0.183. So the probability of getting response of yes is almost 18.3%. Okay, what is the interpretation? There is a 0.183 probability, meaning if you convert this decimal into percentage, it's actually 18.3%. There is a 18.3% probability that a randomly selected adult says that they have seen or been in the presence of a ghost. Okay, so we talk about the probability of an event, and whenever we discuss about the probability of an event, there is a complement of that event. which we denote by this notation called A bar. Let's say A is an event, then A bar means it's opposite of A. Okay, for example, let's take same example of coin. There are two event, head and tail. Then complement of head is tail, complement of tail is head. So head and tail are complement of each other. The complement of an event A, denoted by A bar, consists of all outcome in which event A does not occur. So remember, probability of event, the complement of event A is actually 1 minus probability of event A. Complement, because we know that total chance is 1. So, if you add probability of A complement and A, then it should be 1. Probability of head and its complement tail is 1, because when you flip a coin, then there must be either head or tail. Okay, so this is the relation between probability of an event with the complement. So probability of any event plus its complement, probability of its complement is always equal to 1. Okay, in a Pew Research Center survey of 2002 randomly selected adults, 1,782 of those respondents said that they use the internet. Find the probability that a randomly selected adult does not use the internet. So there are two different ways we can answer this question. By looking this, we can directly find out how many of them they don't use internet. 2000 minus 1782. So if you subtract that, you're going to get 220. They do not use the internet. So probability of not using internet is 220 divided by 2002. Okay, that's the one way of finding. But you can also answer this question by finding how many of them said they use the internet. So you can find the probability of using the internet, which is 1782 divided by 2002, and to get this answer, subtract that value from 1, and that will give you the 0.110. Okay, the real event rule for inferential statistics. Real event rule: if under a given assumption the probability of particular observed event is very small, and then observed event occurs significantly less than or significantly greater than what we typically expect, with that assumption we conclude that the assumption is probably not correct. So here is the rule. Let's assume that for the significantly high number of success, let's assume that X success among N trial is significantly higher if the probability of finding X or more is less or equal to 5%. That's called 5% rule. And similarly, X success among N trial is significantly low number if probability of finding X or fewer is less or equals 0.05, which is 5%. If anything is, less than 5%, then that's significantly low. Okay. So let's do the review here. This is the notation we use for probability of for any event. This is the notation we use for its complement. And remember, probability should be in between 0 and 1. And if something happening is very, very impossible, then probability is for that event is 0. And if something happening is for sure certain, then probability is 1. Okay. Now odds. So here we're going to discuss about the odds. The actual odds against event A occur are the ratio. So if you want to find out what is the odds of happening of any event A, for that you have to find out the probability of happening that event A and divide the probability of not happening that event A by probability of happening by A. This ratio gives you the actual odds against event A. Okay, actual odds against event A. Similarly, the actual odds in favor of A. In this case, you find the probability of event A. Okay, so actual odds in favor of event A. can be found by using this probability of A divided by probability of its complement. And there is another terminology called payoff odds. The payoff odds against event A occurring are the ratio of the net profit to the amount bet. So payoff odds against event A can be found by finding the net profit is to amount of bet. To understand this, let's see one example: actual odds versus payoff odds. And let's say this is the example we're talking. If you bet $5 on the number 13 in a roulette, your probability of winning is 1 over 38 because there are 38 possibility. Number 13 is one of them, so it's a 1 over 38. But the payoff odds are given by the casino as 35:1. That's the ratio they use, payoff odds. Now, these are the questions we'd like to go over. Find the actual odds against the outcome of 13. So there are 38 possibility. So what is the actual odds? How much net profit would you make if you win by betting $5 on 13? And the last question is, if the casino was not operating for profit and then payoff odds were changed to match the actual odds against 13, how much would you win if the outcome were 13? So first of all, probability of finding 13 is 1 out of 38 because there are 38 possibility in roulette. And probability of not finding 13 is 37 over 38 because there are other 37 possibility other than 13 itself. So what is the actual odds against 13? By using the formula, it's a probability of not finding 13 divided by probability of 13, which is 37:1. That's the answer for part A. Part B, because the casino payoff odds against 13 are 35:1, that means which is net profit is to amount bet. So there is a $35 profit for each $1 bet. That's the meaning of this payoff odd. 35:1 means $35 profit for each $1 bet. But in our case, there is a $5 bet. So you have to multiply 5 times 35 to get net profit, which is 175. The winning bettor would collect 175 plus the original bet, which is altogether $180 for a net profit of $175. So that's the answer for part B. How much net profit would you make if you win by betting $5 on 13? So that means it's a net profit of 175. But the casino, if the casino were not operating for profit, then the net profit should be 37:1, which is actually, if you multiply $5 by 37, it should be 185. So instead of 175, in the fair game, it should be 185 net profit. But the casino works for profit, so they should keep some margin. That's why they only give 35:1 payoff. Okay, so let's look at some examples from this section homework. Let's say, okay, this one. Let A denote the event of placing $1 straight bet on a certain lottery and winning. Suppose that for this particular lottery there are 2,592 different ways that you can select the 4-digit. 2,592 different ways that you can select the 4-digit in this lottery, and only one of those 4-digit number will be winner. What is the probability of what is the value for probability of A? So A means winning. So there are 2,592. Only out of one, one of there will be one winner out of 2,592. So the probability of winning for the event A is 1 out of 2,592. But remember, keep in mind, you need to put your answer into decimal form. And here we are using up to 5 decimal places. Okay, I'm going to use a calculator here. 1 out of, let me use my TI-83 calculator. It's 1 out of 2500, 2592, 2592. It's here you have e to the power negative 4. That means after decimal there are 4 zeros, so that means it's a point 00. Let me just, okay, so the value is 1 over, as you can see, it's a 2592 is 3.85802 e to the power negative 4. It's actually after decimal, you are dividing this by 10 to the power 4. If you use another calculator like this, 1 divided by 2592 is 0.00033858. So here it's actually after decimal, you have to go to the 3 zeros. E to the power negative 4 means because to the left there is 1 digit, so if you divide this number by 10 to the power 4, this is what you are going to get. So when you try to answer this question, you have to round it to the 5 decimal place. So rounding to the 5 decimal place, as you can see here, it's a 0.00038. So if you round it to the 5 decimal places, it should be 39, 0.00039. Okay, so the answer is 0.00039. Okay, so what is the probability of complement? Remember, probability of complement is it's a 1 minus this value. So the value we have got here, what is that? Here, just subtract this value from 1. Subtract this value from 1. What is that? So 1 minus the answer means this value, that gives you the probability of complement, 0.99961, 0.99961, 0.99961, which is actually the probability of if you go to the complement, it means out of 2592 possibility, the complement is 2591. That's how you can find this. So let's say another one. Find the probability that when a single-sided die is rolled, the outcome is 4. So as we know, there are 6 faces on a die, and it's a single face. So that means one side on each face. So there are numbers 1 through 6, 1 2 3 4 5 6. So there are 6 possibility. Out of 6 there is only 1 4, so 1 out of 6, so that's the possibility. So find the probability that when a single 6-sided die is rolled, the outcome is 4. So it's 1 out of 6, but we have to express our answer to the 3 decimal place. So 3 decimal place means it's a 1 out of 6, which is 0.166. 3 decimal place, it should be 0.167. 0.167. Find the probability that when a coin is tossed, the result is tails. So remember, in a coin there are 2 possibilities, head and tail. So when you toss a coin, the probability of getting a tail is 1 out of 2, which is actually 0.5. If you divide 1 by 2, that's 0.5. Finally, find the probability that when a 6-sided die is rolled, the outcome is 25. As you can see here, only there are 6 sides, so we can go up to 1 to 6, and the possibility of getting 25 is none because there is no 25. So it's 0 out of 6, meaning the answer is 0. Okay, let's look at another example. Assume that 2200 birds are randomly selected and 2107 of the birds are gulls. Use subjective judgment to describe the number of gulls as significantly high, significantly low, or neither significantly low nor significantly high. Without calculating this, you can see that out of 2200 birds, 2107 is a very huge number. That means, based on this, we can assume that it's a significantly high. So the number of gulls is significantly high based on this assumption only. Let's go to another example. In a test of sex selection technique, results consisted of 223 female babies and 15 male babies. Based on this result, what is the probability of a female being born to a couple using this technique? So, using this technique, out of the result consisted of 223 babies. 223 babies. Out of 223 babies, we have 15 male babies. No, the result consists of 223 females and 15 male babies. So altogether, there are 223 plus 15 babies. So if you add 223 plus 15, that will be 238 babies. Out of 238 babies, there are 223 female. So the probability of having female using this technique is 223 out of 238, which is very high. The probability that a female will born using this technique is approximately this. Since we want to round our answer to the 3 decimal places, so 223 divided by 238, which is total number of cases, it's a 0.937 if you round it to the 3 decimal place. 0.937. Does the technique appear effective in improving the likelihood of having a female baby? Yes, based on this one. Let's look at another example. The sample space listing the 8 simple events that are possible when a couple has 3 children is, these are the 8 different possibilities. After identifying the sample space for a couple, this B stands for boy, 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 girl, boy, and all these possibilities. After identifying the sample space for a couple having 4 children, find the probability of getting 4 girls and no boys. Okay, so if you keep repeating this type of thing, for 4 babies, as we can see here, there are 16 cases. Like you could have, girl, 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 girl. That's a one case only. But altogether, if you just go, girl, 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 boy, that's the second one. Girl, girl, boy, girl, that's the third one. If you keep repeating like that, you are going to see 16 different cases. So the only one case will have 4 girls out of 16. So the probability of having 4 girls out of 16 is 1 out of 16. So the answer, use comma to separate answer as needed. Okay, identify sample space. So we need to find out all these, the possibility. It's not probability. We need to find out the sample space, meaning we need to write down all these possibility. Okay, so it could be girl, 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 girl. So I'm going to type that thing here. Okay, so it could be girl, 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 all girls, and girl, 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 boy, girl, girl, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, boy, girl, boy, boy, girl, Just try to create all these 16 possibility. Boy, 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 girl, 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 boy, girl, girl, boy, boy, girl, boy, girl, boy, girl, boy, boy, and it's boy, boy, girl, girl, boy, boy, girl, boy, 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 girl, boy, 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 boy. So these are the first 16 possibility. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16. Yes. Okay, find the probability of getting 4 girls and no boys. That's a 1 out of 16 as we discussed before here. And we want the answer in decimal form. So 1 out of 16. 1 out of 16 in decimal form is 0.06. Type an integer or a decimal form. Do not round. It's 0.06250. 0.06250. Yes. Okay. Let's look at another example. Fill in the blank. The dash for a procedure consists of all possible simple events or all outcome that cannot be broken down any further. That's called sample space. The sample space means it's collection of everything, all the possibility. Let's look at one more example here. The classical approach to probability requires that the outcomes are equally likely. To have a classical approach, you must have equally likely events. Okay.